Hello students, this is the place where we left the class yesterday because we were interrupted by the power failure. So we are going to start from the same point. We have on display the global stiffness matrix, which has been obtained by combining the local stiffness matrix of two elements. We have taken a problem consisting of two elements. Both the elements happen to be linear. Therefore, both elements have two nodes each. And to add to the simplicity, the current example which has been taken has only 1 degree of freedom for every node, which means that every element has a degree of freedom of 2, which in turn means that there are only 3 degrees of freedom, or you can say that 3 unknowns, which are present in the entire solution process. So corresponding to this, since we have 3 unknowns, we have a set of 3 linear simultaneous equations, which are supposed to be solved together. And in fact, they can be solved using any popular routines such as Gauss elimination or inversion process to give you the value of u1, u2, and u3 in this particular case. The other point to be noticed is that this particular matrix happens to be a square matrix. Of course, it is a symmetrical matrix also. And if you just find out its determinant, you will notice that the determinant also happens to be 0, which basically means that we cannot find the inverse of this matrix. Therefore, even if we know the value of forces acting at the nodes, you cannot really find the value of corresponding displacements. Now, it has already been discussed that a matrix which happens to be a singular matrix, it represents rigid body motion of a body. By rigid body motion, I means the motion of a cycle or a motion of a ball which has been thrown. It has some linear motion, it has some angular motion, and the entire body moves as a whole without undergoing any deformation. It simply moves from one point to another point, but the body is in fact intact. So obviously, since this particular body is going to undergo deformation only when it is constrained at some locations. Therefore, to solve these singular metrics, we are going to impose some boundary conditions before it is going to be solved. One more thing which has to be noticed and perhaps has been discussed in the previous examples was that the terms such as terms which appear in the leading diagonal, that is the diagonal which starts from first row, first column, and goes all the way down to third row, third column. This is a leading diagonal. And the other diagonal happens to be the trailing diagonal. So all the terms which appear in the leading diagonal, they happen to be positive. In fact, they are always going to be positive. And the reason for this can be argued, such as if supposing u2 and u3 both happen to be 0, then obviously it means that the first equation reduces to F1 is equal to K1 multiplied by U1, which basically means that both forces and the deformation, force F1 and the deformation U1, are going to act along the same line. If both of them are acting along the positive x-axis, if force is acting along positive x-axis, deformation is also going to act towards positive x. And if the force is acting along negative x, So the deformation is also going to act along negative x. Cases such as force acting along positive x and deformation acting along negative x really is not possible from the physical viewpoint also. Therefore, the value of all the terms in the leading diagonal are always going to be positive. Apart from this, the diagonal, the matrix happens to have some other properties also, and those we are going to discuss later. But what can be easily be noticed over here is that if you look at the terms appearing in the third row and third column, you will find that there is a term such as K1 plus K2. K1 obviously corresponds to the stiffness of element number 1. K2 corresponds to the stiffness of element number 2. And in fact, if you just happen to look at the discretization, you will notice that element number 1 and element number 2 happen to have a node 3 in common, which basically gives us a global stiffness matrix of the type which is on display. The row 3 and column 3 are going to have contributions from both the elements. This is going to be a peculiar phenomenon which is going to observed in all global stiffness matrix. All the nodes which are common to elements corresponding to this in the global stiffness matrix, the locations are going to have contributions from more than one elements. Like we have just seen over here, the row 3 and row 3 and column 3 has contributions from element number 1 and element number 2. Now coming to the next topic, that is, we are going to talk about the assembly process. We are going to talk about how the local stiffness matrix are going to be assembled together, resulting in a global stiffness matrix. So we have the domain on display. We have the global stiffness matrix given by question number 1. And then we simply write the corresponding degrees of freedom, U1, U2, and U3 in the global stiffness matrix. Similar to this, we have the local stiffness matrix. We have the local stiffness matrix for element number 1, and we have written the corresponding degrees of freedom. This is in equation number 2. And for element number 2, we have the equation number 3 with the corresponding degrees of freedom. So with the help of the degrees of freedom being labeled in the local stiffness matrix and the global stiffness matrix, we simply are going to substitute the local stiffness matrix into its corresponding places in the global matrix, such as the term K1 in the column and row represented by U1 has been kept in the column represented by U1 in the global stiffness matrix. So you can simply transfer the local terms from local domain to the global domain, as has been illustrated over here. A second example corresponds to the term represented by the column which is U1 and the row which is U3. This is in the local domain, and it has been kept in the corresponding place in the global domain. So similarly, coming to some other example, element number 2, the term appearing in U2 and U3 has been kept at the corresponding place in the global stiffness matrix. Now kindly notice that the two terms appearing for element number 1 and element number 2, they are going to be placed in the same location in the global stiffness matrix. This is primarily because the node number 3 happens to be common to element number 1 and to both of them. So this basically gives us a set of rules which are supposed to be followed for transferring the stiffness matrix from local domain to the global domain. And we are going to follow this particular example in the future classes also. So this is it. Now coming to some general discussion regarding the topic of stiffness matrix. The thing is that we have developed a stiffness matrix for a case of a spring. So obviously it means that there are going to be some persons, there are going to be some students who are going to think that since a spring has an inherent property known as its stiffness, therefore the matrix which is called stiffness matrix is going to be derived only for those bodies which are elastic in nature. But the thing is that the stiffness matrix is only a terminology which in fact should be interpreted as a mathematical relationship existing between nodal degrees of freedom and the corresponding disturbing parameters acting on the nodes. Stiffness matrix should simply be interpreted as a mathematical relationship between the nodal degrees of freedom and the corresponding disturbing parameters acting on the nodes. So obviously, if you interpret this thing with respect to the spring which we have just discussed, nodal degrees of freedom, obviously it means deformation, displacement, and the corresponding disturbing parameters acting on the nodes represents forces. So in the present example, the stiffness matrix represents a mathematical relationship between displacements and forces. So if you just change your viewpoint, you can very well realize that this particular relationship exists in some other structural cases also, such as a prismatic uniaxial bar which has a spring constant given by AE by L, or a prismatic circular cross-section bar which is undergoing torsion. The spring constant in this case happens to be G, J by L, where the terms which are being used have the normal meaning. But a term such as A, K by L, which exists in one-dimension Fourier one-dimension conduction case, is also going to be termed as a stiffness matrix. Though the mathematical relationship in this particular case is going to be derived between temperature, which happens to be the nodal variable, and heat sources or heat sinks, which are going to be the disturbing parameters. And similarly, for a non-structural case, such as fluid flow through a porous medium, we have a corresponding stiffness term defined as A K by L. Thus, the stiffness method can be applied to non-structural problems such as heat transfer, for which we are going to start from the Fourier's law of heat transfer, fluid flow, for which we are going to use the Darcy's law, as well as electrical networks, for which the Ohm's law is going to be used. Now we come to a most important topic in the curriculum, in the entire curriculum of the finite element method, which happens to be the potential energy approach to derive the stiffness equation. Now, the advantage of potential energy approach is that it is a more general method than compared to the direct stiffness method. It is more adaptable to determine the element equations for complicated elements, such as those elements which have large degrees of freedom. The thing is that compared to the direct stiffness method, which we have just used previously, the potential energy approach, the potential method for deriving the stiffness equation happens to be a more general or more widely used method of finding the stiffness equations. Whensoever we are going to have large degrees of freedom of an element, it becomes very difficult to find the stiffness equations using the direct method, which was just illustrated. But for these cases, we are going to use the potential energy approach, and we are actually going to develop the equations for plane stress and plane strain element, which basically are going to be the area element. And area element means as simple as a triangular element having three nodes, one at each corner. So the simplest triangular element is going to have three nodes. But the thing is that in this particular case, the deformation can be along two axes. It can be along x-axis also. It can be along y-axis also. Therefore, the degrees of freedom for each node are going to be 2. And since there happen to be 3 nodes, each element is going to have 6. Each triangular element is going to have 6 degrees of freedom. Of course, there are higher variants of triangular elements also, but this has just been quoted at the present point for the discussion point of view. So for the case when we are dealing with plane strain or plane stress problems and we are taking a triangular element, we are not going to use the direct approach, but we are going to apply the potential energy for the formulation. Similarly, cases of axisymmetric loading, plate bending, and three-dimensional solid stress elements. For all these complicated cases, we are going to use the potential energy approach. So from the theoretical development point of view, we are going to illustrate this particular approach using the simplest example possible. So we once again take the example of a spring having 2 nodes at the locations and forces acting along the positive x direction at both the nodes. The stiffness of the element, the stiffness of the spring obviously happens to be K. So in potential energy approach, we basically try to find the energy of the total energy of the spring. So the spring basically is going to contain energy because of its deformation. So that is the energy because of its straining, its energy because of its deformation. And the other part of the energy which is going to be involved is because of the forces acting on the spring itself. So the potential energy basically consists of two parts. One part is energy because of straining, the other part of the energy is because of the forces which are acting on the element. So the first term, that is half K, that should have been U1 minus U2 square. U1 minus U2 is the deformation of the spring, and half kx square basically is the energy associated with this particular spring deformation. And similarly, F1 U1 and F2 U2 are the energy associated with the forces acting at node number 1 and node number 2. So this becomes the entire energy of the system, that is the spring, which has been expanded. Now the thing is, since we are trying to minimize the energy of a system, we are going to differentiate the expression of the potential energy with respect to the unknown parameters. Since the unknown parameter are 2 in this case, represented by U1 and U2, we are going to differentiate equation number 1 by U1 and U2 one by one. That is going to give us two linear simultaneous equations, and those two equations are then going to be kept in a matrix form. So this is the entire process or the entire theory behind the potential energy approach. So we differentiate it with respect to U1 first, which gives us the equation number 2. Differentiating it with U2, giving us equation number 3. Cutting out some common parameters and keeping them in a matrix form gives us the same equations which were obtained using the direct stiffness method. So this is a simple illustration which has been used for demonstrating how the potential energy approach is going to be used for finding the stiffness matrix of an element. Now we are going to apply all the theories developed so far for developing the stiffness matrix of a truss, which basically is a member, is basically a bar member for which the equations have already been discussed. But in the present formulation, we are going to derive the equations of the element using some more general discussions. So in the present section of the lecture, we are going to derive the stiffness matrix of a bar element. Bar and truss basically are two words which are going to be used interchangeably, but they represent the same member. We are going to illustrate how to solve a bar assemblage by the direct stiffness method. Here we are going to take a solid example and we are going to discuss that. We are going to introduce some guidelines for selecting displacement functions. This is a topic which is going to be done for the first time so far. Now, as a next step, we are going to transform two vectors which are basically inclined to each other, but the two vectors are present in the same plane. This is going to be of use when we are trying to assemble two or more than two bars which are present in the same plane, but they happen to be inclined to each other. So this transformation is going to be of useful for solving the bar problems which happen to be oriented at different angles. And then we are going to talk about the methods which are going to be used for evaluating the stress. And one of the last point is going to be the demonstration of stiffness. We are going to discuss how stiffness can be used, how symmetry can be used to reduce the complications, to reduce the size of a problem to be solved. As a further step, we are going to solve some problems which have inclined supports. And then we are going to solve the bar using the theorems of minimum potential energy. Now, obviously, the solution which has been achieved using the finite element method, that requires to be validated, that requires to be compared with the exact solutions. So we are going to do that also. And then we are going to talk about something about the Gallatin's residual method, which has been applied to the case of a bar element. We are also going to introduce some other residual methods applied to the simple case of bar element. So the first step is the selection of the element itself. In fact, this particular step happens to be common to all the FEM formulations. You always start by choosing an appropriate element, which in this case is a bar, that is a spring element. So we have a bar undergoing some tensile loading, and in the same figure, we have the forces and the deformations at the two nodes, which have already been shown. And please note that there happens to be a coordinate system also, and both the forces, both the deformations acting at present at point number one, node number one and node number two, are have been taken along the positive x-axis. So this basically is a representation of forces from the FEM point of view. So the next step is define the relationship between stresses, strains. The strain displacement relationship is given by a formula as simple as this. If you know the nodal deformations, you can very well manipulate them to find the value of strain. And obviously, stress when multiplied by cross-section area gives you the tensile force acting on the member. So manipulating these two equations, you get a relationship between tensile loading and the deformation of the bar. And using the sign convention, which we have seen, which we have just seen in the previous slide, you notice that the force acting at node 1, in fact, is equal to minus T, where T happens to be the tension. And similarly, force acting at node number 2 happens to be equal to T. So this gives us two equations which we can substitute, which you can represent in a matrix form, and a common parameter AE by L has been kept outside, which basically represents the stiffness of the bar. So this is the general step which have been followed for the case of a structural element. You simply start with a relationship which exists between stress and displacement, and then you have another relationship between stress and forces. You simply keep all these terms together, manipulate them slightly to give the stiffness equation, which is on display. Obviously, a term such as AE by L is analogous to the spring constant term K for a spring element. Now, the selection of displacement function in step 2 of the derivation of stiffness matrix for the one-dimensional bar element. This particular step we have missed. In fact, if you just rewind the video, you will observe that from step number 1, we have directly shifted to step number 3. In fact, in between, there is a step number 2, which is missing over here. And this step we are going to discuss at the present location. We must choose in advance the mathematical function to represent the deformed shape of a bar element under loading. So actually, before starting the FEM formulation, you should have a mathematical representation, mathematical formula, which is going to represent the deformed shape of a bar under loading. For example, it is a common observation that when a bar element is going to be elongated, it will simply deform along the directions in which the forces are acting. So this is how the member is going to behave under tensile loading. But the thing is that when the same member is under compressive loading, so obviously its length is going to reduce because the forces are trying to compress the member. But if you go on increasing the compressive force, there is going to be a position, there is going to be a situation when the member is going to buckle. It is going to be compressed only to a particular extent of forces, but after the forces exceed a particular limit, the member will actually buckle. And this buckling basically is a phenomenon which is observed in columns, particularly in columns which happen to be of large length and small cross-section area, which means that the column is slender. So the thing is, we are now talking about two different phenomena, both under compressive loading. And these two phenomena happen to be represented by a mathematical formula. So the thing is that if you make a formula only for the compressive loading and do the entire formulation, the thing is that even if you go on increasing the applied force, the member will simply compress, but it will not show any response of buckling, simply because that particular buckling has not been incorporated incorporated as a mathematical formula. So the net outcome of this FEM formulation is going to be wrong. The thing is that you might be working at a particular force for which the member is going to buckle, but the FEM analysis is simply not going to show any buckling simply because the mathematical formula corresponding to buckling has not been incorporated. So the thing is, you should always have an idea. You should always have an idea of the possible response of the system so that it can be properly accommodated, it can be properly incorporated as a mathematical expression in the displacement equation. So this point becomes very necessary. Unless you are able to incorporate this particular response, all your FEM formulations are going to be wrong. Most commonly functions used are polynomials. In some cases, we do use trigonometric functions also, but those are rare. Most of the time, we simply used polynomials simply because polynomials can be easily differentiated and integrated. And the simplest polynomial, of course, happens to be a linear polynomial given by our expression u is equal to a1 plus a2x. In this, a1 and a2 are the two unknowns. So a linear polynomial has 2 degrees of freedom given by a1 and a2. And this expression is going to be slightly modified in a way which we have already discussed in the previous classes. But simply for the sake of completeness, those steps are repeated over here. We evaluate the value of u at the location of node number 1, which is 0, simply giving us u1 is equal to a, which is one constraint equation, where u1 is the deformation at node number 1. Similarly, at node number 2, where the value of x happens to be capital A, we get the second constraint equation, from where we can find the value of a2, which is the expression on display, u2 minus u1 divided by length. And then we are simply going to substitute the value of a1 and a2 into the initial linear polynomial which we have chosen. And then we are simply going to adjust the form of the expression to the one which has been on display. And at this moment, we are going to introduce two factors or two functions given by n1 and n2. n1 is 1 minus x by L and n2 is x by L. So u, which is the deformation, basically reduces to u1 n1 plus u2 n2. And please notice that n1 and n2 both happen to be linear functions of x, because we don't have any powers of x in these two expressions. And this is primarily because we started with a linear polynomial, u is equal to a1 plus a2 into x. So we started with a linear polynomial, we end with another form of linear polynomial. But both these two expressions basically are the same expressions. The n1 and n2 are basically going to be known as shape functions. They are also known as interpolation functions. This is because they express the behavior of the assumed displacement function over the domain of the element. Hence are known as the shape functions, as they determine the type of behavior over the domain of the element. In this particular case, since we are talking about a line element, the line element is going to be represented by the domain of the line element is going to be represented by x coordinate only. Since both the shape functions happens to be linear shape functions, so obviously they are going to have a straight line behavior. The other thing which is to be noticed is that the value of shape function number n1 has a value 1 at node 1 and it has a value 0 at node 2. This can simply be found by substituting the value of x in the equation. For node number 1, x is 0, so that gives us the value of n1 to be 1. But at node number 2, the location happens to be L, which is going to give you the value of n1 to be 0 at node number 2. In a similar way, you can plot the graph or the variation for the other shape function number n2 also. And at this particular point, we are going to conclude that every node is going to have a particular shape function associated with it. Every node is going to have a particular shape function associated with it. So node number 1 is linked with shape function number 1. Node number 2 is linked with shape function number 2. And the other point which is observed is that the value of n1 is going to be 1 at node number 1. It is going to be 0 at the other node. Similarly, the value of n2 is going to be 1 at node number 2. And it is going to be 0 at the other node. Now this particular observation is going to be of immense importance when we are going to derive the shape functions of other complicated elements. Other complicated elements such as those which are going to be used in one dimension. In one dimension, I can have a 3-noded element, a 4-noded element, and things like that. In 2 dimension, we are going to talk about area elements such as quadrilateral having 4 sides or a triangular element having 3 sides. It is also going to be possible that a triangular element is going to have more than 3 nodes such as 4, 5, 6, 7, 8, etc. And similarly, a quadrilateral, a simplest quadrilateral is going to have 4 nodes at the 4 corners, but more higher variants of quadrilateral are going to have higher number of nodes, anywhere from 5, 6, 7, 8 to a number such as 14, 15, and things like that. So when we are going to talk about all these complicated elements, this particular variation, these properties of the shape functions are going to be of immense use at that particular point. Now this paragraph is important. The thing is that every FEM process is going to give you the value of the unknown at the nodes itself. Every FEM process is going to give you the values of the unknown parameter at the nodes itself. But what if you require the value of the unknown parameter somewhere in between 2 nodes? So in that case, we use the interpolation functions. The n's are often called interpolation functions and can be used to interpolate the value of a function between the given nodes. Now the properties of the 2 shape functions have been illustrated in a tabular manner. x is equal to 0 and x is equal to L happen to be the two locations of the nodes. We have node number 1 at x is equal to 0. We have node number 2 at x is equal to L. And the corresponding values of the two shape functions n1 and n2 have been depicted in a tabular manner. But the thing is that the shape functions are supposed to satisfy several other properties also. They have several other requirements also, which we are going to discuss in the coming slides. Conditions of shape functions. Now, what is going to be illustrated over here are going to be some points, some common observations which these shape functions are supposed to satisfy. But the thing is that the students are supposed to go through the books or the other sources available to them to have a detailed understanding, to have a thorough understanding of the shape functions. So the first requirement is that the shape functions should be continuous within the element. The simple linear function of u is continuous within the element. We are talking about the continuity of the linear function within the element and not outside the element. Therefore, the linear function yields a continuous value of u within the element and prevents some phenomena such as openings, overlaps, and jumps, because the function itself happens to be a continuous and smooth. By terms such as opening, the thing is when you are loading a member, cracks do not appear in the member unless you are actually modeling cracks or wrinkles. They do not actually appear in the system. Wrinkles basically means overlapping of the domain itself. And opening, obviously, it means cracks. So unless you are actually modeling these two phenomena, the entire body, the entire element is supposed to constrain. It is not supposed to constrain, it is supposed to deform as a continuous member. So obviously it means that a particular mathematical expression which is going to represent this deformation should also be a continuous function. That means because the actual member deforms as a continuous medium, the mathematical expression to be used for representing this response should also be continuous. And obviously more upon this is going to be discussed when we are going to talk about the Jacobian. The approximating function should provide inter-element continuity for all degrees of freedom at each node of discrete line elements. So the thing is that in the present point, that in the previous point, we were talking about the continuity within the element. Now we are talking about continuity between two elements. And since we are talking about a line element, two line elements are going to be in contact at a particular point. So that means that the mathematical equation should be continuous at that particular point only. That is inter-element continuity. And the thing is that when loading is being done, two contacts, two elements actually do not break contact. वो नोड जो शुरू में कॉमन थी, the node which was common between the two elements is going to remain common between the two elements even after deformation. It does not cracks. Therefore, the mathematical expression should provide for the condition of inter-element continuity for all degrees of freedom at each node. And this simply means that the node which is common should have the same value of deformation for both the elements. The node which is common to two elements, it should have the same value of deformation for both the elements. Obviously, if the common node has two different values of deformation corresponding to two different elements, it means that the node has broken. There is a crack which has appeared in the domain after the deformation. So this is what is meant by inter-element continuity. For the bar element, we must ensure that nodes common to two or more elements remain common to these elements even after deformation, and thus prevents overlaps or voids between the elements. So in this particular figure, we have node number 2, which is common between element number 1 and element number 2. Of course, both the elements have a different polynomial which represents the deformation within each element. But the thing is that the value of deformation at a point which is common to both the elements, it should be same from both the expressions. Now, if the linear function satisfies both these continuity, that is continuity within the element and continuity between the two elements, then the function is going to be called as a conforming or compatible equation. This is simply because it ensures the satisfaction of continuity between the adjacent elements and continuity within the element. Of course, when this continuity condition is extended to area elements or to three-dimensional elements, we can have similar conditions in these cases also. When two area elements are in contact, the contact is going to be on a particular line or a particular curve. So all the nodes which are lying on this common curve, should have the same value of all degrees of freedom. And similarly, when we have two volume elements in contact, the contact is going to be over a particular area. So all the nodes which are lying on this common area should have the same value of deformation for both the elements. In general, a symbol Cm is used to describe the continuity of a piecewise field, such as axial displacement, where the subscript m indicates the degree of derivative, that is inter-element continuous. Thus, a field variable is C0 continuous if the function itself is inter-element continuous. The field variable is said to be C1 continuous if it has both its field variable and the first derivative continuous across the common boundaries. And corresponding to these examples, the beam and plate element happen to be C1 continuous because they are going to enforce the continuity of displacement as well as the derivative of the displacement, which is more commonly known as slope. These are the two continuities which are going to be enforced across the common boundaries. Now come into some other aspects. The approximating function should allow for rigid body displacement and for the state of constant strain within the element. The mathematical formula which has been chosen to represent displacement, it should allow for rigid body displacement and for the state of constant strain displacement within the element. And this we are going to discuss in detail. The first term A1 in the mathematical expression, in fact, is the term which allows the rigid body behavior of the element. And how this is going to do so, that we are going to see in the coming slide. The second condition of constant strain means it has some physical significance also. The thing is, if we go on reducing the size of the element, there is going to be a condition when the element is going to become such a small element that you are going to assume that the entire element undergoes constant strain. It has a value of constant strain, same strain throughout the element. So this is what is meant by the second requirement. The term A2x allows for constant strain because when you differentiate this term, you get A2, which basically is a constant. This state of constant strain in the element can occur if the elements are chosen small enough. The completeness of a function is a necessary condition for convergence to the exact solution. The conditions which we have just discussed, most of the element, kindly notice, most of the elements, not all elements. most of the elements are going to satisfy these conditions, and thus the FEM solution which you get is going to converge to the exact solution as the process of mesh refinement is taking place. Now, this is depicted with the help of a graph. If you choose elements which have the appropriate displacement function, now as the number of elements are going to increase, your FEM is going to give you a solution which is converging to the exact solution. Please notice that the FEM solution is going to converge to the exact solution, but the FEM solution itself is not going to give you the exact solution. It only gives you a solution which converges to the exact solution as the number of elements are increasing. And depending upon the application, whether the application happens to be critical or whether the application happens to be non-critical, you can actually define your acceptance level. You can actually define your tolerance. Tolerance basically is the margin of error which is acceptable to the according to your requirements. So if you desire that your FEM solution should be more close to exact solution, you can specify a tolerance level which is very low. But if you are modeling phenomena which happens to be non-critical, by non-critical I means where maybe human life is not in question, or maybe phenomena such as rockets which are critical, or phenomena such as missiles, airplanes, all them happen to be critical. So here you are going to define a lower value of tolerance. So you get a solution which happens to be more closer to the exact solutions. But some phenomena such as designing a cycle, or maybe designing a cricket bat, these are some non-critical areas. So you can actually work with a larger value of tolerance. The idea that the interpolation function must allow for rigid body displacement means that it must be capable of yielding a constant value. Now the thing is that if an element is is behaving as a rigid body, obviously it means that there is no deformation present. And since there is no deformation present, it means that the value of displacements at both the nodes should be same. And since the value of displacement at both the node is same, it basically means that anywhere within the body itself, anywhere within the element itself, the deformation is going to have that same value. So when the value of deformation is same throughout, it basically means that the body is not deforming. So this can be, this exercise can be done mathematically also. So let's assume that the constant value is A1. Therefore, U is A1. The deformation is U, which is A1 in the entire domain. And in the next line, we have U1 is equal to U2, which basically means that the deformation is same at both the two nodal locations, which gives us A1 is equal to U1 is equal to U2. which basically gives us n1 plus n2 is equal to 1. n1 and n2 obviously are the two shape functions. So the summation of two shape and n1 and n2 are two shape functions. They are linear polynomial expression in terms of x, and the summation of these two is equal to 1. So obviously this means that at any point in the domain, that at any point within the element, the summation of all the shape functions should come out to be equal to 1. And if this is coming out to be 1, it basically means that the mathematical polynomial which you have chosen allows for a rigid body transformation. So this is where we are going to stop the lecture at the moment. In the next slide, in the next lecture, we are going to discuss the potential energy approach to derive the elemental equations for the bar element.